Good morning, everyone. Welcome to the WATERAGRI scientific webinar on research results for sustainable farming. My name is Sebastian Pucuek from Lund University, and together with my colleague, Rolf Larsson, who is a coordinator of this fantastic project, we will be your hosts for today's event.
Thank you very much, Sebastian, and thank you all for joining. We are in the lovely old Bishop's house on Lund University campus. You saw the exterior maybe on the little short film clip before we started. This building is from 1845. Lund University was actually founded in 1666. Today we will share with you some of the research results that aim to enhance sustainable farming practices across the globe, which has been the focus of our WATERAGRI project. And I'd like to say a special thank you to our keynote speakers, Ariana, Alba, Harian, Arkadiusz, Tamara and Ida, all from different countries in Europe. And also thank you to our technical team from Lund University for making this webinar possible.
Thank you, Rolf. We are streaming live to the WATERAGRI YouTube channel. The recording will be available later. And we also encourage everyone to engage with us through the Menti application during the Q&A session. So in the agendas, you will have the link to the Menti and the code. This code will be also shown on the screen below during the keynote presentations. Let's proceed with today's exciting agenda then. So after a short introduction of the project by Rolf, we will have first keynote by Riona Kanga from Alchemia Nova on biochar research for nutrient retention in agricultural waters. And then we will have a first Q&A session. You can use Menti during the presentation. Next, we will have Alba Canet Marti from University of Natural Resources and Life Sciences, Boku, and on simplified modeling as decision support tool. Followed by Harry-Jan Henriks Fransen from Forschungszentrum Jülich on models updated with measurement in near real time provide stakeholders with better information for their management. The next keynote will be Arkadiusz Głogowski from Wrocław University of Environmental and Life Sciences on how satellites and modeling supported with lab and field experiments lead to cooperation with farmers. The next one will be Tamara Avalon from University of Oulu, talking about assessing the sustainability of WATERAGRI solutions using the example of the water retainer product and farm-constructed wetlands. Last but not least, we will have Ida Sarnowska from Agriculture Advisory Center in Brwinów. Ida will talk about WATERAGRI massive open online course on WATERAGRI solutions. And we will close the meeting very shortly after 12. Next, I'd like to invite Rolf, who will provide an overview of the WATERAGRI project. Rolf?
Thank you, Sebastian. So I will use the next few minutes to give you a very brief introduction to the WATERAGRI project. I think I'll need my glasses here. So WATERAGRI is a research and innovation project supported by the European Union via the Horizon 2020. And our project is very much focused on sustainable agriculture with special focus on retention of water and nutrients, while still keeping in mind the importance of food production for Europe. So it's also about food security in a way. Our research project is quite large, and it's centered around 19 different solutions for water retention and nutrient retention. And the applications are primarily at a farm scale. So we're looking at a rather small scale while still keeping also in mind that the farm is a part of a larger river basin. The project has been going on for 4 years. We started back in 2020 in May, and we're gonna be finishing formally in a few days from today, at the end of April. The kickoff meeting was actually in Lund in May in 2020, but we had to endure with the COVID pandemic during the first 2 years, which was, how can you say, a little bit of strain on the consortium, but we came out with good, and then we could manage to have physical meetings after that. The work is organized around 10 work packages with different work package leaders across Europe, and we have to deliver 54 reports during the project time, and we have a few to deliver next week. And as I already mentioned, we have partners and colleagues all over Europe, and we actually have 23 partner organizations across Europe representing 12 different countries. And the organizations are of different types, like universities, research institutes, and SMEs. And we also have a number of case study sites, because this is an essential part of what we're doing. We're developing and testing innovations and different solutions for water retention and for nutrient retention. And those solutions have been tested on our different case study sites. All solutions have been tested, all case study sites have been utilized, but not necessarily have we tested all solutions at all study sites. And as you can see from this map, we had case studies in many countries in Europe, sort of going from the north in Finland. And we also had a case study site very close to where we are sitting right now, just about 10 or 15 kilometers north of here in Sweden, called Stånga Nygård. And then we have, as we move down southwards in Europe, we have case study sites in France, Germany, Poland, Switzerland, 2 different sites in Austria, actually 3, also in Italy, and then not to forget Hungary, in the so-called Pannonian zone, which is I think, European Union invention with these Pannonian zones. But it's a so-called biogeographic zone with special characteristics. So that's why it's essential to also have a case study in Hungary. That was extremely brief introduction of the WATERAGRI project, but since we have been working in 4 years, it's really impossible to go through everything we have done, and we will have some example presentations later on. The main focus of this webinar, and you will get some interesting results from some of all those solutions, some of all that work that has been done. And we decided at a very early stage that the final conference of WATERAGRI project would actually be in the form of 3 different events. So this is the final one today. We started with a conference in Brussels on the 6th of March, where the theme was linking water and agricultural science to policy, which was I could say a very successful event, where we managed to reach out to the European Commission, where we also had speakers from the Commission. And we raised a big interest in the results from our project. The second conference was aimed at our stakeholder group of farmers and also the general public. This event was called Sustainable Agriculture by Research, and it was also announced during the so-called Lund Sustainability Week, which is the host of a great number of meetings across various topics. But our WATERAGRI research was one important part of this Sustainability Week. That happened, as you can see here, 10 to 11 April, just 2 weeks ago. And now today is the final event. Now we're mainly reaching out to the research community in Europe. And the theme of today is research results for sustainable farming. As I said, we'll give you some appetizers about the research we have done within WATERAGRI. I would like to take this opportunity to thank all the WATERAGRI partners, and I hope some of you are online now, watching this and listening into this webinar. I also want to thank all the WATERAGRI stakeholders which helped us develop our project and to evaluate with a friendly and critical eye all the work we have done. Stakeholders from various categories, farmers, advisory services, policymakers, etc. And also another thank you to the WATERAGRI Advisory Board, who also helped us improve the work as we went along during these 4 years. So thanks to everybody, and I'm ready now to give back the word to Sebastian.
Thank you very much, Rolf. I strongly encourage to visit our website, which consists of all the results, all the information, all the public deliverables. Everything will be soon over there, including a link to this recorded meeting today, also recordings from other meetings related to the final conference, WATERAGRI final conference. Okay, so let's start with our first keynote speaker. And our first keynote speaker is Ariona Kanga from Alchemia Nova. Ariona will discuss biochar research for nutrient retention in agricultural waters. So please, Ariona, the floor is yours.
Good morning, everyone. I am Ariona Kanga from Alchemia Nova, which is based in Vienna, Institute for Circular Economy and Nature-Based Solutions. And together with another colleague, Mona Arnold, we will present today biochar research for nutrient retention in agricultural waters. As Rolf introduced before, this research is part of WATERAGRI project. I cannot move the slide, sorry. Yes. So this presentation today is about WATERAGRI case studies and research focused on the biochar. The biochar research overview under WATERAGRI was very vast and interdisciplinary, and also including comparative research. It included laboratory tests, where we did batch experiments. 3 partners were involved and did comparative batch experiments for different types of biochar. Column experiments were carried out as well from a master student at Boku University. Pot experiments were as well conducted from Hungarian partners to see how bioavailable is the phosphorus which is retained in the biochar. Then we did also pilots in the field, which included nature-based solutions applications in several countries in Europe. And this included bio-based multi-layer filters, drainage filters, constructed wetlands. As well, there have been has been application of biochar in the field in order to test the water retention capacity of the biochar, and as well the circularity aspect, using it as a fertilizer. And altogether comes incorporated then in simplified models or different models that you will hear during today's talks. So the issue in our agriculture waters especially is that they are a source of contributing into the eutrophication of the lakes and even the oceans. And there has been already now evidence that the intensive agriculture and the exponential use, let's say, of the consumption of fertilizers, nitrogen and phosphorus in particular, contribute to this high storage of nitrogen and phosphorus in the soil. And once we have rainfall and precipitation, these nutrients can be leached into the water through two pathways from surface runoff in agriculture and from the subsurface drainage water. And both of these pathways contribute into the eutrophication effect, which is illustrated also into this picture from NASA. It is a satellite image of the large blue-green algae blooms in the northern parts of the Baltic Sea. So what are the possible solutions? One solution is to limit this fertilizer input, which has already been put in place through regulations, but we have, of course, a background amount of these nutrients in the soil, which do not limit the effect of eutrophication. So one approach is to implement nature-based solutions before of the end of pipes. So before the agricultural waters end into the streams and lakes, we need to maybe apply nature-based solutions, and this we tested in the WATERAGRI project because these nature-based solutions are inspired and powered by nature. They address societal challenges and resolve problems, and they provide multiple services and benefits. As well, they can be effective and economic, efficient. So focus of this presentation, I will not focus on all the research done on the biochar, but only on the laboratory part, so batch experiments, and I will provide two examples of pilot studies, two pilot studies in Austria, in Lower Austria. So we looked at ecological and cost-efficient media for nutrient uptake and focused our research on the circular role of biochar. And we will provide examples of nature-based solutions addressing agriculture runoff, so the first pathway, and the subsurface drainage water, the second pathway that contributes to eutrophication. And we use for this biochar, but also other substrates. Why using biochar? Biochar has been investigated and researched vastly the last 15 years probably, and it is a carbonized biomass obtained from sustainable sources like plant biomass, waste material. It is a porous material, which means that it can have potentials to retain the water and the nutrients in the soil. It has also adsorptive qualities in terms not only of phosphate that we investigated in this project on nitrogen, but also it has been researched for its effects on pesticides and herbicides and heavy metals immobilization. It is used in agriculture and it provides several benefits. It is a supply for plant nutrients. It can increase crop yield. It can act as adsorbent, and this is something that we tested. And it can improve also soil physical chemical properties and reduce greenhouse gas emissions. But there are different types of biochar. There are a lot of types of biochar, and not all of them will give the same results. In order to increase the efficiency of this material in relation to phosphate and ammonia nitrate retention, it can be activated. And there are two types of activation: physically activation and chemical treatment. The physical activated biochar, which was done in WATERAGRI, it is supposed to increase the absorption capacity, and the chemical treated coating of the biochar can contribute through the chemical aspects which increase the affinity of certain ions. So we tested both this kind of biochars. We tested different types of biochar, and here are represented their commercial names. Pflanzenkohle, it is originated from grain husks and fruit sludge and wood shavings. Güllekohle, it's originated from wood shavings. Biochar is another biochar, and magnesium coated biochar with magnesium hydroxide. And of course, there were also other substrates which are used in these nature-based solutions applied in the pilots. One of them is the zeolite. Okay, so some of the results with relation to the physical activation of the biochar. We observed that the activated biochar, and this physical activation is done through applying steam and water flow at high temperature, 800 degrees Celsius. So the activated biochars had always resulted in an increased specific surface area. And this means that there are more sites available for phosphates, for example, to absorb into this porosity. So always these high levels of specific surface areas are very good when we talk about properties of the filter materials that are used in constructed wetlands or any other filter technologies. And this was evident and very significant. So activated biochars had an increased specific area compared to the non-activated ones. And this resulted also in an increased total porosity. In terms of retention of different nutrients, so ammonia, nitrate, and phosphate, we observed that activated güllekohl biochar had high absorption compared to the original, so non-activated one. And the same was noticed for the activated Pflanzenkohle. But there is a difference between the activated Güllekohle and activated Pflanzenkohle. Some biochars can leach phosphate, and this is related to the origin of the product. Because also the phosphorus or phosphate is part of the plants as well, right? So then we pass here in the comparison between chemical treated, so the coated biochar with magnesium hydroxide, in comparison with the non-coated biochars and the zeolite. Magnesium hydroxide coated biochar performed better compared to the other materials, so Biochar and zeolite, in terms of phosphate. 98% of the phosphate concentration was removed, and the concentrations varied from 0 to 25 milligram per liter. So these are all batch experiments. There were good removal rates also for in terms of ammonia and nitrate. And what are the suggested mechanisms for the absorption of ammonia, nitrate, and phosphate? Phosphate, we suggest that, or the research suggests that it is chemically, it precipitates in the surface of the biochar, and in these porous spaces that we talked about earlier. And as well, nitrogen is absorbed by the original and the thermophysical activated biochars in the pores. So we have adsorption from one side and also adsorption plus precipitation for phosphate. Some conclusions for the biochar, it's that there are different types of biochar, and their removal rates for nitrogen and phosphate can vary widely. And this depends on the origin of the biochar and how it is treated or not treated physically or chemically. And all the biochars that are physically and chemically treated perform better than unmodified biochar, but this will increase the cost, of course, for larger applications. And now I would like to pass you through two pilot examples where, again, we used biochar. And the two pilots, the first one will was built to treat agriculture runoff. So every time that there is heavy precipitation and this agriculture runoff may contribute to leaching of nutrients into the surface waters, we need solution for this aspect, as well as the second pilot. It will discuss the subsurface water. So it was built to treat the water coming from the drainage pipes. Both sites are located in Austria, and I will call them Pilot 1, Mistelbau, Pilot 2, Gleisdorf. So the first pilot, it's a bio-inspired multi-layer filter. It operates catching the surface runoff in agriculture context, and the water percolates vertically in these different layers of substrate, and it is treated and retained. And so we tested these different type of materials, first in the lab in collaboration with other partners, VTT and BOKU, and then we made the application in the pilots. So there is an agriculture land which is connected with the three pilots. The water is collected first from the agriculture land, is led by gravity to our systems, and then the effluents are monitored continuously for 2 seasons, for 2 years. Here are some pictures from the field case study in Austria, and different parameters were monitored, including nitrate, ammonia, phosphate, pH, and conductivity. The results show that all 3 filters behaved similarly for phosphate retention with effluent concentration below 0.5 milligram per liter. And nitrate drain garden, which was one of the filter tested, and biochar filter had some variability with soil retaining better nitrate. And the ammonia were below detection limit. The 3 systems consisted of drain garden, one, the second was biochar, and the third was a control only with soil. Okay, sorry, I forgot to mention this. The second pilot. In the second pilot, we addressed the subsurface drainage water. And the catchment area is 1 hectare. And this is an organic farm in Gleisdorf, in Styria, in Austria. And there is subsurface drainage, which is all collected, and the outlet is in this picture that you show. So this is the red one is the main drainage pipe, which collects from smaller subsurface drain water. And here in this location, or in this pipe, we installed a 3D printed structure, which was filled with adsorbent. The first structure contained zeolite, and the second contained biochar. They are inserted into the pipe, and they are monitored as well for 2 seasons for the same parameters as in the first location. There, we should take in consideration for field applications that the flow is always variable also in times, so in different seasons, but also in terms of quantity, so in volumes. Therefore, the challenge is that these filters that we choose for such solution, they should fulfill the requirement of hydraulic conductivity, so to have big grain size in order to allow the water to pass through the system, but as well they need to have also these chemical characteristics and high specificity surface areas in order to retain nutrients. That's why we combined these two materials, because zeolite has bigger grain size than the biochar. And it was a journey also for the biochar. We had a fine biochar at the beginning. It didn't work well, but then we ordered biochar. We produced a biochar which was originating from the cherry seeds in order to mimic these granules, and it was coated with magnesium hydroxide. There were some good results. However, it needs more monitoring, and these are only preliminary results. The first filter, zeolite, provided hydraulic conductivity and nitrogen and good nitrogen removal. And from the research, it is well known that the zeolite is very good for nitrogen removal. While from the second filter, we had the advantages to retain phosphorus, because the magnesium hydroxide coated biochar, as shown also from the lab tests, has this potential. So my take-home, or our take-home messages are that agriculture runoff and subsurface drainage water contributes to eutrophication. Biochar, there are different types of biochar, and the removal rates of nitrogen and phosphorus can vary widely. So we need to be careful to pre-study and pre-select well the characteristics of the biochar to be used. Modified biochar, physically or chemically, increased higher the removal efficiency of these nutrients compared to unmodified biochar. And there are innovative systems that can tackle agriculture runoff and drainage water issue before the water is discharged into our surface waters using these reactive substrates. At the end, I would like to thank all the team involved in this research and project. And with that, I conclude my presentation. Thank you very much.
Thank you very much, Iriona, for that insightful presentation. We will now begin our Q&A session. You should be able to see in a second the code for the Menti on your screen, or maybe you see it already. But I know that Rolf has a question.
Hello, Ariana. Thank you very much for the presentation. We got a question here about the application of these biochars in relation to the, let me see here, in relation to the, how can you say, efficiency of these biochars and the price. Is there any special types of crops that are sort of suitable for applying these biochars?
Yeah, so there are like two questions in one. I'll address the first one. Every biochar which is chemically or physically activated, let's say, will increase the costs of this biochar. And the farmers might have difficulty actually to buy and to apply in large scale these activated biochars. We will need to see for which properties a farmer would use the biochar, and then take the decision. And the price is sometimes 2 times or 3 times higher than the normal biochar in order to have good results for phosphorus retention. And with regard to the second question, from a scientific perspective, so if I would choose biochars that needs phosphate retention in the context of the application in a nature-based solutions, it's important to select a biochar which provides from substrates that are granular. For example, the cherry seeds were a good option because they can provide the hydraulic properties, but also the chemical properties being coated.
Thank you, Riona. And we have a question from Mr. Jacek Kluska from Polish Academy of Sciences. Did you analyze functional groups of biochar?
functional groups. I'm not sure what the question.
Maybe we will ask for
But
more clarification on
we
the.
analyzed the different types of biochar as I showed in the presentation, and not only different types of biochar, so providers, but also physically and chemically treated biochar, and we compared with the untreated ones.
Thank you, Riona. Let's open, still leave the Menti open. And of course, if you have a question a little bit later to our previous keynotes, maybe we can come back if we have a little bit more time.
I have one more question.
We have another question, yep.
I have one more question here. So the question is about the biochars. Some of the biochars you used, or maybe all of them, seem to be commercially available. So the question here is about information about those characteristics which you have investigated. Are they available to the consumer, or how can they find out about the characteristics of those biochars?
Yeah, all the biochars are available, commercially available, except the magnesium hydroxide one, the chemical coated magnesium hydroxide biochar, because this was ordered, let's say, and then specifically produced for our project. But there can be many biochar providers that can have similar characteristics. Yeah.
Thank you very much, Riona. We don't have more questions at the moment. So let's move forward. Thank you very much.
Thank you, my pleasure.
Okay, so we're moving ahead to the next presentation. But first, let me say to those of you who might have joined after we started that we are slightly ahead of schedule. But let's move on to the second presentation. I'm very pleased to introduce our colleague from BOKU, the Institute for Bodenkultur, as we used to say in English, University of Natural Resources and Life Sciences. And we give the word to our colleague Alba Kanemati. She will present on the topic simplified modeling as a decision support tool. Alba, please go ahead.
Thank you, Wolf. I hope you can see my slides. Yes, my presentation. All right. So good morning, everyone that is watching. I will briefly talk about the simplified modeling as a decision support tool. As a brief introduction, I would like to say, I'm a researcher at the Institute of Sanitary Engineering and Water Pollution Control at the University of Natural Resources and Life Science, Vienna, known as BOKU. And I'm also a PhD candidate finishing the PhD in the doctoral school, Human River Systems in the 21st century. I consider myself an environmental scientist that fell in love with treatment wetlands and modeling. And I studied at the Universidad Politécnica de Valencia in Spain, where I'm from. And then I ended up at BOKU. Here we go. So what are the simplified models? In WATERAGRI project, we consider these simplified models as part of the modeling framework, and they are decision support tools. So not decision-making tools, because they are designed to support us as rough estimation, not in detail. So what are they for? They are designed to help the stakeholders to know if a solution is or a method is beneficial for them or not. And we give these average values, these rough numbers. Why? Because these solutions are tested in a case study under specific conditions, so like climates, for example, or in soil texture, but they may not work under other conditions. And then the stakeholders that want to know if that's also good for them, then they can also get this rough estimation. So in WATERAGRI, we have different solutions, and we couldn't build a simplified model for all of them. So some solutions is just not applicable. So for example, the Agri Lemma series game, that's a board game. There are other solutions, as Eliona just explained us. Those are technologies that are still under development. We're still gathering data. So we don't have enough data to build such a simplified model. There are other solutions that they are already simplified. And we ended up in 3 solutions: farm constructed woodlands, tracer methods, and the biochar for water retention that we could build the simplified models. So I will focus today in one solution, the farm constructed woodlands, and one method to gather information, the tracer methods. All the solutions have informative fact sheets that you can find in the website that will give you information about the cost benefits, the description, how it works, etc. So starting with farm constructed wetlands for nutrient removal and water retention. In WATERAGRI, when we say farm constructed wetlands, we mean free water surface wetlands, or also known as surface flow constructed wetlands. Constructed wetlands in general are these engineered systems or technologies that use these purification processes that happen in wetland ecosystems and to treat the wastewater. And they build the technology to maximize these processes. There are different types of constructed wetlands. In this case, as I said, we talk about the surface flow constructed wetlands, so the water doesn't go through the filter media, but moves freely, and that's because they deal well with pulse flows and changing water levels. In these wetlands, then, without this whole filter media, they can also hold water if we, for example, make them impermeable. In agricultural fields, in agricultural catchments, they are very good to minimize, to treat fertilizers, for example, and also pesticides from the runoff water. And they are very good at sedimentation. So, for example, when we have erosion from the field, we can also keep it in these systems before it goes to the streams. And it's good for nitrification, denitrification. In this picture, you can see the wetland that is in the Italian case study included in the project. And we used their data to build up the simplified model for 3 reasons. So it's a constructed wetland that has been running for more than 20 years. It's large scale, so we have good data, not only lab data, and it's event-based. So we tested the simplified models in different events that had different conditions. So for example, water that was running more like smoothly and continuously, or an event that was kind of flat. So we could test how robust the model was. And so for you to understand a little bit, this model, to model the constructed wetland, has 2 parts. So one is the hydraulics, and the second is the kinetics. So the hydraulics is how the water moves through the wetland, and the kinetics is how the total nitrogen is degraded. In a study we modeled the different combinations. So the transport, which is the hydraulics, the degradation of the total nitrogen is the kinetics, and also under steady and steady conditions. We did compare all the combinations, and we ended up with the best hydraulic part and kinetics. For the audience that is familiarized with the constructed wetlands and designing of constructed wetland, they know that this is not new. We tested it under the different conditions, which was very interesting. And we did it only for total nitrogen, which means that it's like a pool of bacteria, and the total nitrogen removal is temperature dependent. So this formula that you see below, that's how it looks, the background of this simplified model. This is the study that was published 2 years ago. And this is how the model looks like in the user interface in the project. So if you go to this link, or you can find it in the website, then you can link, you can tick or choose a location, and then automatically you get average temperatures of every month. And you just have to add, you have to know how much water comes to the wetland, also the concentration of the total nitrogen, more or less. You can have a rough estimation if you didn't measure it. Also the available area that you have to build the wetland, and also the shape of the wetland, if it's longer or if it's more like a square, and also the depth. And we can get more information about the parameters if we click on them. So, for example, if we don't know the concentration, we can get estimation, or the same with the inflow, how to measure it or how to guess it. And yeah, and this will change over the year, and because it's temperature dependent, as I said before. And we move to the tracer methods. Tracer methods, I call them as a fingerprint in soil for water. And in WATERAGRI, when we say tracer method, we mean water. So water, the water that moves throughout the water cycle is an environmental tracer, and it's stable, so it doesn't degrade, doesn't change. So it changes throughout the water cycle, as I said, but because of fractionation processes, which means that so if we have a lake and water evaporates, the water that remains has a different composition. So what do I mean for this composition? Water has, what we learn is that the molecule is H2O, right? And this H2O is, so the hydrogen and the oxygen, they are chemical elements. And we learned that the hydrogen has 1 proton, so it's hydrogen 1, but there are also hydrogen with a neutron in their nucleus, which would give us the deuterium. And that's a heavier isotope, so because it has more neutrons in the nucleus. And that also happens in oxygen. When we measure the ratio, so we learned that this that the hydrogen and oxygen, they are only like 1 and 16, because they are 99% of the oxygen and hydrogen that is in nature, but there are also the others. And when we measure this ratio, then we can get a lot of information. How? So, for example, in Europe, the precipitation water has a different composition depending on the season. So in summer, we will have more enriched in heavy isotopes precipitation, and in winter, we will have more depleted precipitation. These differences in the composition, we can also see it, we can observe it in the soil profile. So the theory behind it is that the new water, the precipitation, pushes the old water downwards, and it keeps more or less the same composition, the same isotopic composition. And that's why we can also follow it. And then we can link this, for example, if we sample in May, we take the sample in May and we can see, for example, in the soil also, we can check, we can identify the winter precipitation at, for example, 30 centimeters or 40 centimeters deep. And that's how it works. So These are the very easy, this is this method to gather the information, and this is how it works. It's 4 steps. First, the sampling. Second, we analyze the soil water, so the water content that is in the soil and the isotopic composition of the pore water. And then we find this peak to compare it with the composition of precipitation. And finally, we quantify with the formula that you see. This D, so what we quantify will be, for example, the groundwater recharge or the potential groundwater recharge or the mobile soil water. So it depends on the data that we have, then we can guess, so we can quantify more specific water fluxes. And when we do a balance, that we can also, for example, know the evapotranspiration. This gives us information. So when Eriona before said that there are those 2 pathways, so we have the runoff, but we also have the leachate. And when water leaches, when water flows, it also can take some nutrients with it. And that's very interesting for us to know how it works, so we can prevent leaching, for example, or we can manage much better. What we did is a study that was published last year to test this simple method to quantify the water fluxes in the fields under different tillage and different irrigation systems. So 4 tillage and 4 different irrigation systems. This was very interesting because we could see differences, and with only applying this method that doesn't need exhaustive monitoring of the field. Once we know that this method works, we wanted to know the differences in the isotopic profiles in the soil under different climates and also under different soil textures. So to get an idea about this difference would let us know when would be the best time to take a sample, for example, or the frequency, or how, so we can better use this method. This is an example. So we did the simulation study in Vienna and the different soil textures. And for example, when we went to the field, we took the sample, and we can observe that the soil was silt loam, and the sample was taken end of spring. So we could identify that this nadir, this peak, the winter peak, or the minimum was in the same, more or less in the same depth. So it works. And this is an example of how we could see it in our webpage. So this is an example of Dansk in the north of Poland. And this is how, so the same precipitation would look like under different soil textures. So clay, silt, loam, loamy sand. And we can then say, okay, so when would be the best time for sampling, also depending on the soil, or in frequency, or in which interval. So if we have to take samples every 5 or 10 centimeters. And these are the 2 parts of the tracing methods. So first, the simplified model itself, so the peak shift displacement method that I explained. And the second, so the sampling recommendations that we can provide in WATERAGRI. And that's it, actually. Thank you very much.
Thank you very much, Alba, for a very clear presentation, as always. We have some questions for you here. First question is about how you have tested these simplified models, because this is meant to be used by stakeholders. So did you test these simplified models with stakeholders? And what, if you did, what is the feedback you received?
We did. We tested it with them. It's still, for example, the tracer methods, it's the stakeholders that may be more interested in it are scientists, and that's something that we see already the method is applied, and we will see also in the future. We are presenting it in conferences and so on, and that's a more it's a slower process, right? But the farm constructed wetlands we did, and they find it very interesting. It's very interesting for them to see that they can directly go to their location and see how it works, and also that it's so easy to use. So we still need to add some last features in the user interface, like, for example, the water that could be able, like potential water retains in the wetland if it's impermeable, or the total in tons per year total nitrogen removed or retained in the wetland. But yeah, they're happy, and like there's potential also for improvement in the future if we gather more information.
Okay, thank you. We received another question here about the simplifications, because these are simplified models. So could you mention some important simplifications that you did with these models?
Simplifications. Yeah, well, some important simplifications. For example, for the constructed wetlands, a model can be very, very complex, needing many parameters, for example. And in this case, for example, the hydraulics, it works you cannot test continuously in each meter how the total nitrogen is degrading, but you get a rough estimation. And what the model does is to divide the wetland into pools, so equally distributed or equally sized pools. And then the water goes into a pool, it mixes completely, it degrades a little bit, it goes to the next pool, and so on. And that's a very interesting feature, because the real wetlands, they are very complex. So they also have like dead zones. They also have like the first part of the wetland may degrade faster. There's a higher concentration. There's more going on there. They may get water more frequently than the end of the wetland that sometimes could be dry, or yeah. And what the model does is to make it homogeneous. So it's a simplification that has the pros and cons, right? But that's the interesting part, because we cannot. So a farmer or a stakeholder cannot gather so much data forehead. So before even designing the model, before implementing and constructing the wetland, that's the interesting part, that they can get this rough estimation before without having those numbers, those parameters.
Okay, thank you. I think we have another question.
Yes, we have a question on the Menti. Could you repeat where this wetland is located, who is operating it after the project, and whether it is possible to organize the study visit there?
Yeah, this is operated by the colleagues from the Canal, I don't know if I will pronounce it well, but the Canale Emilia-Romagna in Italy, in Budrio. It's near Bologna, and also monitored by the colleagues from the University of Bologna. And I think you can go and visit them if you arrange the visit with the colleagues from Canale Emilia-Romagna.
Yeah, it's a very big research station, and I think they're organizing visits and conferences over there. So it's a very nice place. We strongly recommend everyone to go approach and visit them. Okay.
Maybe we should say to the person asking this question that we can provide contact information to our colleagues in Italy.
Also, if you go to our website, to partners, you should search for a partner with the acronym CER. CER. As Alba said, it's a very long Italian name. Sometimes it's hard to pronounce for the non-Italian speakers, but you will find the partner CER. Okay, thank you very much, Alba. We don't have any other questions.
Thank you.
And let's continue with the next presentation. So our next keynote will be Harjan Hendricks Fransen from Forschungszentrum Jülich. Harjan, I hope that I pronounced this name correctly. After 4 years, I should already know how to pronounce it. Harjan will discuss how models updated with measurements in near real time provide stakeholders with better information for their management. So over to you, Harjan.
Thanks, Sebastian. And I try to start my presentation.
Thank you very much for joining. I've heard that you just caught some nasty flu, and thank you very much for being with us today.
Yeah, Corona again.
Oh, even worse.
At the conference. So yeah, I'm in home office here. And yeah, can you see the presentation now? You see it in presentation mode?
Just a second.
Now? Okay, thanks. Then let's start. Yeah, so this presentation is about models which are updated with measurements in near real time, so to provide stakeholders better information for the management. So yeah, we are from the Agri Institute, Forschungszentrum Jülich in Germany. In fact, there are more people involved in this work, and I only listed now the 2 persons, myself and the postdoc Richard Hoffmann, which was working on this in the last years. Oh, yeah. So the motivation for the work is that we see in Central Europe the tendency that summer precipitation decreases with less water availability. On the other hand, we have an increasing water demand related to higher temperatures, also more need for irrigation, for example, in agriculture than in summer. Cost that would increase for irrigation, and then the risk of increased yield loss. So we explored here models that can help to optimize the irrigation system and to minimize cost, then reduce yield losses. And so these models will be used for predictions, let's say, especially in the next 2 weeks, based on all the information we have. So to help stakeholders like farmers. So this is the system we are dealing with, a terrestrial system. So this represents the water cycle. So water flows in the soil, groundwater, evapotranspiration in the rivers. But in this kind of model, we have also the energy cycle. So this means, for example, heat transport in soils, so soil temperature is simulated, and also nutrient cycles, so carbon, nitrogen, and the growth then of vegetation like agricultural crops. So these are integrated models of the terrestrial systems. And what we did in this project is to create a data model pipeline. So on the left, you see data. So we have measurements here in the fields, as shown, for example, measurements of soil moisture, of evapotranspiration, of carbon fluxes. But we can also have measurements, for example, by satellites that can be used, or for example, measurements by drones. So all this kind of information could be used. In the middle, then we have this integrated terrestrial system model with infiltration of water in the soils, growth of crops, groundwater, and so on. And we combine this in an optimal way, and we can create a product like the one shown on the right. So that is here the simulation of the plant available water over the region. So when we start to set up a model, so in our case, the terrestrial system modeling platform, there are different steps. So one is a conceptualization of the area, and to set up this model then. So this conceptualization includes, for example, to include in the model how this region where you set up the model is related, let's say, to the surroundings. And then this is transferred into a software or a code, and we have then a numerical simulation model that makes then these calculations and calculates the states of the agricultural watershed or the agricultural fields. So that includes then soil moisture contents in the fields at different depths, near the surface, deeper groundwater levels. It includes also the crop state, so for example, the leaf area index of the crop, and it can also include then the amount of, for example, nitrogen in the soil, and for example, nitrate amounts which percolate towards the groundwater. So that's all included in these calculations. We can compare these calculations then with the measurements and see whether they are more or less realistic. So this is not yet a data simulation, but before setting up a model, we need to check that the model is not too far off the reality. So after this comparison with the measurements, we could consider to reconceptualize the model. For example, include additional processes which are necessary, or to change some parameters to have a higher correspondence between simulated values and measured values. At the end, if this model more or less works fine, it can provide information for the next day, and also for predictions then for the next weeks. For example, if we use or if we drive those models with weather forecasts. And these predictions can be made available online, and we can have graphs and tables and so on, which show the results of those simulations. So that's the model. Now we have also the data that are combined with the model. So you see here the principle of data assimilation. So what happens in data assimilation? So in data assimilation, we do not run this model now one time, and one has a certain prediction with the model. No one runs the model many times. So for example, 100 different model runs that give 100 different results. And these 100 different model runs represent then the uncertainty that we have. Because for each model run, we use other input data, for example, other meteorological data, because we have uncertainty on those meteorological data. For example, because we have uncertainty in the weather forecast. And we use maybe different soil properties and vegetation properties because we have also some uncertainty there. So we consider now the uncertainty in these model calculations, and we can calculate from this ensemble of model runs a model covariance matrix that characterizes this uncertainty. On the other hand, we have then measurements, and these measurements have also a certain uncertainty that we know. And we combine now measurements and model runs. So in this figure, you see here, for example, on the left, the model values, and at some point in the middle, at the time point tk here, at the time point tk, we see these predictions for the model states, and we have this observation, which is a bit different from these simulated values. And this observation is now used to correct these model predictions. You see that then on the right, there's this correction. But there's still the uncertainty. So we have still different values for the different model runs, because this observation is also not perfect, and maybe it's a bit further away from the point where we make the prediction and so on. So there's still uncertainty, but the observations allow to correct the model prediction so that the model is closer to reality. And in this correction, it takes into account, on one hand, the uncertainty that we have regarding the model predictions, but also the uncertainty and the representativity of the measurement. So we tested this, for example, at our WATERAGRI test site in Saalhausen. You see this here. It's located in the western part of Germany, quite close to the border with the Netherlands and Belgium. You see the agricultural fields around Saalhausen, and we have there then different data types like meteorological measurements. We have also weather forecasts, for example, for the German Weather Service or the ECMWF that we can use. there's information on the soil and the crops, and there are different types of measurements like soil moisture, soil temperature, and also other measurements like evapotranspiration and net ecosystem exchange for carbon. Then, you see here such a measurement site. So in one, you see that a meteorological station. The green thing, the larger green thing there in the middle is a cosmic ray Newton sensor that is able to measure soil moisture over a larger area, not just locally, but an area with a radius of 250 meters. And there are also in situ measurements here of soil moisture and soil temperature. And there are other type of measurements located in this area. So this is just here one example. Yeah, then we go back to this pipeline of information. So on the left, we have the measurements. They are connected to the internet and the Internet of Things. And with a cellular network, the data is transmitted to a collector, and then with OpenVPN, it goes to a server. So there the data arrive, they are stored, they are further processed, and the data can also be used in the modeling. And so these models can also run in the cloud then, and they can answer then specific questions from stakeholders like farmers and other stakeholders, and provide then results. So as a first step, we can also visualize these observations in real time. So the meteorological observations, these measurements of soil moisture, soil temperature, and so on. So you see this on the right, for example, in the upper row, we have here air temperature and relative humidity represented in red, air temperature. And for this example period at the end of March and February and the beginning of March, it was already very warm. It's not from this year, but in that year, in the end of February, it was already close to 20 degrees. But then in the beginning of March, it was again in the night below 0, for example. So you can see this then. And you see further variables on the fourth row, for example, precipitation. In this case, there were only a few millimeters of precipitation in that week, so quite dry. And the lowest two rows are for soil moisture and soil temperature then. Sorry. So we now go back to the data pipeline again. On the left again, we have our Internet of Things. All information is collected in the clouds. We can visualize the measurements, what I just showed, but then we can do also the simulations there, and these model simulations, the forecast, and also then give this information to end users like farmers, but also agricultural chambers, also more regional organizations that operate at a larger regional level. So objective is then to have optimal predictions of the states of crop and soil, like soil water content, for the next 2 weeks, and combine then these online measurements, the simulations with the model, and the data assimilation to have this end user friendly online visualization, and all this information should support decisions in near real time for agricultural watersheds. So for our specific simulation experiments in Zellhausen, what we needed to do is a long span up of 1,000 years. So that sounds maybe a bit so strange, but this is necessary in the simulations to stabilize the nutrient pools like carbon and nitrogen for these type of simulations. And then we can do 2 types of simulations to compare results. One is an open loop simulation, which means that we do this ensemble of model runs. So we have a larger number of model runs that characterizes the uncertainty, but we do not use measurement data. So these model runs are only driven by the uncertain meteorological forecasts. So we can get forecasts for the next 2 weeks, but we do not consider now measurements that we have. And then we compare this with simulations where we use measurements. And in this case, we assimilate measurements of soil moisture. And we do also predictions now. But the difference is that we incorporated the measurements that we have today, our situation today. So in this case, the soil moisture measurements. So we expect then that our predictions for the future are also improved because we have a better characterization of the conditions that we have today. So these type of simulations we can compare. And I think I already indicated this. Our model input data are then these meteorological data. This is what we need, but we also need data on the soil type, the crop that we have. And also, it's of course better if we include information on the agricultural management. If there has been irrigation, maybe the last week already, that would be important to include, and also information on fertilization. We use also then the official weather forecasts for the next 10 days. And like I said, these data are stored in the cloud then. The measurements are stored also there, and they can correct these simulations using the data assimilation procedure. We can also use other measurements that are not assimilated to compare with observations. So it means those observations we do not include, but we only keep them also to evaluate how our model performance is. So here's one example for the Zellhausen site for the year 2022. In red, we have measurements of soil moisture with cosmic ray Newton sensor. We see it's quite dry in summer, soil moisture goes down to 20%, but it's not, in this case, very dry. So there is some impact of the drought on the crops, but it's reduced. It's not very dry like, for example, 2018. In blue, you see also the model runs. So they are sometimes a bit further away from the measured values and often quite close. In this case, we do not see so much difference between the open loop and the data assimilation run. The data assimilation run only gives slightly lower errors. You can see this in the figures on the right. And then we can compare, we can produce these kind of plots here. This is the soil moisture content at different depths. The upper row is for 1 centimeter depth, and the lower row is then for 20 centimeter depth. And we have here in the different lines then the predictions, open loop and data assimilation of soil moisture. And here are also already plotted the observations that came in later then. So for example, we are here at the time point of the 1st of January. So this line here, left of it is gray, right of it is white. And then we do predictions for the next 10 days using our model and using also the weather forecasts. And we do now, in this example, predictions of soil moisture for the next 10 days, but we can do this for other variables like soil temperature, or for example, the crop status. So how the biomass of the crop would develop. And to make this a bit better for end users, like farmers or agricultural chambers, we propose also a traffic light system here. So site specific, we can determine what would be the right soil moisture content. For example, we can say, okay, between 25 and 35%, that's fine. We do not have problems then. The soil is not dry and also not too wet. But if it's below 25%, our traffic system would go from green to orange because it starts to become dry, and it would be good that farmers start to prepare for irrigation activities and for sensitive crops start irrigation. If it's below 15%, it's red because the crops are in any case then affected by drought stress. So the best would be to irrigate. On the other hand, it can also be too wet, like we have, for example, this spring in the area here in Germany and neighboring regions. So the trafficability of the land is an issue. So we can also, for example, say then if soil moisture content is above 35%, our traffic light system also goes to orange because it's starting a problem is starting with too wet conditions. in that case, it might be more difficult for the farmer to take measures and to change the situation. So we can present, let's say, the output of these simulations also in the form of a traffic light system, also for the predictions then for the next 2 weeks. So the benefits at the end are, first, there's information for farmers, agricultural chambers, and other organizations on the hydrological situation, the crop situation at the farm level or at the level of agricultural watersheds for the next weeks. And this can help to make decisions, taking also into account uncertainties, because these simulations not only give predictions, but also the uncertainty of those predictions. And let's say more specific measures, like specific management interventions, could also be evaluated with further simulations, for example, by consultancy. We expect then that the benefit is that one can optimize the irrigation quantity, so not to irrigate unnecessary, but to avoid yield loss. One can get a better assessment of the different decisions and the impact on yield losses and costs and gains and profits. And it can also help, and that is, but maybe more related to another type of simulations that goes over longer time periods. But that can also be done with the same kind of system to evaluate whether for a farmer it would make sense, for example, to buy better insurance products, because, for example, certain risks are quite high in that area, and he or she could then calculate whether an insurance product would make sense. At a larger scale, for example, agricultural chambers, one can make a more detailed regional drought assessment. So to update, let's say, policies in a more dynamic and faster way using the best information. But this has also costs. So that's a disadvantage, of course. These soil sensors and weather station might cost between 2,000 and 5,000 euros. Specifically, the cosmic ray Newton sensor that measures soil moisture over a larger area costs up to 15,000 euro. But on the other hand, if farmers have a license from the German Weather Service or the ECMWF with more specialized products that those agencies develop, then the costs are also quite high per year. And we provide this model code for free. And so it's an open source model. And on the other hand, commercial codes cost then money. The main disadvantage at the moment is that this approach has a quite high cost because it's compute intensive and would also need to pay costs on the supercomputer. So with that, I come to the conclusion. So we think terrestrial systems modeling can use available online measurements with data assimilation to get optimal estimates of the states of the agricultural system for specific catchments or for agricultural fields, and so predictions of soil moisture, groundwater level, crop state, and so on. And combined with weather predictions for the future, you get an estimate of the best possible estimate of the conditions for the next week. And this can be used then for planning, for example, irrigation or other activities on the land. There's an incentive for a new business model that specialize in translating these model results then into tailored management options and providing long-term quantitative support in agriculture. So we are looking into this, and also in the methods then that can reduce this computational cost. And we think there that to replace in part these model simulations with machine learning methods can then strongly reduce the computational costs, so that these computational costs would not be an issue anymore. And sorry for going a bit over time, and thank you for your attendance.
Thank you very much, Harry-Jan. It's time for another round of questions. I know that Rolf.
We have some questions for you, but first I'd like to make more like a general comment. I think it's very interesting to see here very clearly demonstrated by the talks we have just been listening to by Harry-Jan here, and also by Alba in the previous talk how the great variety of solutions and activities that have been going on in our WATERAGRI project, and it becomes very clear, especially here, I think, when we have the simplified models first, and then we have the quite advanced physically based models as represented in the presentation by Harion. But although they are different approaches, they still have the same general target of providing improved information to farmers in the end, and to make the agriculture, how can we say, more efficient. And here we also have a difference in time scale, while the models that Harion have been talking about is they are geared for the short-term predictions, prognosis over like a lead time, which was mentioned here, about 10 days, for instance, while the simplified models by Alba have a different purpose and might also aid farmers in decision making, but over a much longer time scale. So anyhow, let me turn to the questions. We received some questions here, some with regards to the application of these models, but you basically already answered the questions. So let me move on to some more technical questions. In these models, what you do with the data is correcting the models as you move along in time based on the information from the data. And the question here is about how you actually do that correction. You mentioned updating the state variables in the models. Do you also change parameter values when you do the update?
Yes, we can also do this. It goes a bit in mathematical detail to explain how the update is exactly done. But you have, let's say, differences between measurements and simulated values, and and then to some degree, the simulations are corrected towards the measurements. So let's say if the measurements would be perfect with no measurement error, then at the measurement locations, the model would be completely corrected towards the measurements. But the question is also, if you have a distributed model, what happens with the surroundings? Because this measurement gives then also information on the surroundings. And also in the surroundings, there will be a correction. So let's say you do this for one field, but a neighbor field might have a similar soil moisture content. So this depends on how representative is this measurement. And this is also calculated by the models. So there's so-called spatial correlation. And with help of this spatial correlation, which is also simulated by the ensemble of model runs, let's say also in the neighborhood corrections are made. So these corrections by the measurements are not only made at the measurement locations, but also in the surroundings. And it depends then on one hand on what is the measurement error, and on the other hand, what is the uncertainty in the model simulations. So that's one thing. The second thing, one can also in this framework update parameters together with the states. So that is at the end better, because if you are able to better estimate your model parameters, like for example, hydraulic conductivity, or it could also be parameters which are related to the vegetation, then you have better parameters that, even if you would not have done measurements in the future, would also allow you to have a better model with better model prediction. So we always try to also optimize parameters, but sometimes this is different. For example, if you have remote sensing information, so soil moisture from satellite, then these measurements are less precise. And we see then that it's in general difficult to estimate parameters with that kind of information. So that kind of information can be good to optimize states, to update states of the model, but not precise enough to update parameters.
Okay, thank you very much for this exhaustive answer. Very good. We have another question here, which is also a bit technical, but at the same time more general. You mentioned in the beginning that your model essentially models all the relevant systems, so not only the flow of water, but also the flow of nutrients and also the state of the crops. So could you say, is there any part of this model which is, how can you say, less accurate than the others? Where are the main, how can you say, potential errors in the total model system here? Is that possible to say? Some parts that are more difficult than others to model?
Yeah, that is the case. I think, yeah, for example, this model also simulates, for example, nitrogen and the emission of N2O and the transport of nitrate towards the groundwater. And I would say that, yeah, in that part, this kind of model is less evaluated with measurements, and probably the model error is still higher for example, nitrogen than for, let's say, the simulation of water and simulation of soil moisture and evapotranspiration. Yeah. So roughly one could say that. And this kind of model still has a lot of parameters. And yeah, so that's also a source of uncertainty, and also a lot of parameters related to the crops and the vegetation. So that's an important source of uncertainty as well.
Okay, thank you very much, Harian. So we will move on to...
Oh, we have another question. Sorry.
Oh, okay.
Sorry.
Excuse me.
We have one more
Hang
question.
on, Harian.
The question from the mentee. I'm wondering how you communicate with local farmers, how to convince them using your complex models.
Yeah, that's
always a challenge, right?
Yeah, that is a challenge. Yeah, so we are in contact with them and also with the agricultural chamber. And interesting feedback from them was also, yeah, they are also involved here, that they have, for example, these sensors also installed, and so they are participating and interested. But yeah, a feedback from them was to use this kind of product, this forecast product, then we really need to know that these predictions are very precise. So they were really specifically interested in the predictions and want also to see that the predicted soil moisture, for example, is also close to what is measured. So yeah, I think it's important that they get confidence in this kind of model predictions, and that they see that it's really quite close to reality, so that they can use it for planning. I would say now they are already interested very much in the data and for information, but to really use it in the management, they need to be maybe even more convinced that these predictions are accurate.
Thank you, Harian. I will just follow up on that question. That in this project, by design, we were focusing on constant cooperation and feedback loops from our stakeholders, and of course, farmers were the most important group of stakeholders that we have identified. So we had a series of workshops with farmers, like the big ones, but also each case study was organizing local workshops in local languages, constantly encouraging and informing about the progress of the project, but also about the tools. And so to some extent, all stakeholders were helping to co-create solutions that we produced in WATERAGRI. So that's one of the elements that helps at the end to convince final users for using tools, even if they are very complex at the beginning. Thank you, Harian.
Yeah.
Thank you very much. I think you were at the EGU probably as half of Europe. So can we say that we recommend all the colleagues that came back from EGU from Vienna to check out against coronavirus, probably?
Yeah, I know there were some more infections there. Yeah, so the virus is apparently still going around. Yeah.
Thank you very much,
Thanks.
Harry.
Yeah.
See you around. Thank you.
Okay, so for those of you who are listening and watching this webinar about the WATERAGRI projects, I'd like to point out again that we're slightly ahead of schedule. We're being efficient as ever. And then, so we're moving on to the presentation number 4 on today's agenda. So I'm happy to introduce our colleague Arkadiusz Głogowski from Wrocław University of Environmental and Life Sciences. Arkadiusz will speak on the topic of satellites and modeling supported with lab and field experiments, how they lead to cooperation with farmers. Please, Arkadiusz, go ahead.
Hello, everyone. Do you see my presentation? Do you see me? I hope yes. As Rolf said, I'm Arkadiusz Głogowski from
That's a little bit unexpected. I hope Arkadiusz will come back soon to us. Yes.
Hello.
Yes, we got you again. Okay.
Okay. So I will talk about the work of many people that was involved here and show the results of their work. But I'm just the speaker. I'm just a transmitter of the work of many people that was working over this project over 4 years. Yeah. So what we start with, so our site is located in Southwest Poland, and we start with installing the monitoring system to understand how the processes are going in this field. So the farmer that we are cooperating with have like a farm with more than 500 hectares. During the project, we conduct 2 different experiments with the solutions that was the part of the WATERAGRI consortium. And besides this product, which is the biodegradable water retainer, which was provided by Hungary, we also test decision support system, which was provided by Agricolos, and we basically was focused on using remote sensing data and store them and have them on some kind of a platform that is easy accessible by the farmer. As well, we want to test how this biodegradable products increase the soil water retention. So by testing this product, we take 2 approaches. One of this was set up the field experiment. When depends on the year, we sow different crops with different scenarios, and we apply on the field the amount of the water retainer that was recommended by the producer. In parallel, we was also doing the laboratory analysis, where we want to take different type of soils and test it in different scenarios. So we took the most diverse field that we have on the farmer field. We choose 3 different soil types based on the granulometric composition, and we test them in 4 scenarios without water retainer and with 3 different doses on 2 different experimental setups. And as a result, there was a lot of information that goes into account, but what the farmer was the most interested in is how much water he really saved on using this product and what was the difference in the yield. So to highlight this, depends on the scenarios and doses and the soil, the variety was from 8% to even 48%. And it was also corresponded with yield, and the difference in the crop yield, with in the experiment with the water retainer and without the water retainer also varied between 7% to even 36%. Of course, there was different conditions, meteorological conditions, soil conditions, different years. So it is hard to correlate this, but the effect of this product was always visible, and it was also visible in the physical properties of changes of physical properties of the soil. So the next action that we took in WATERAGRI was to try to analyze the surface soil moisture based on satellite images from Sentinel-1. So we correlated those times of satellite of Sentinel-1 with measuring campaign of soil moisture sampling, and we correlate the algorithm that we was able to capture the surface soil moisture with the in situ, and we make a regression analysis which corresponds very well in terms of spatial distribution. In terms of time distribution, we take those, we use soil moisture measurements, and we extract the grid values from the satellite images that corresponds to the location of the soil measurements, and we analyze the differences of the soil moisture at the moment where there's no vegetation, so there's no crops. And we can see that the correlation of those images corresponds to the in situ measurements is very high, on the level of 0.6 correlation. So this is the actions that was linked to the surface soil moisture. And the next action was to try to investigate if we are able to assess the state of the phenology phase of the crop based on a BBCH scale, which is the European Union index which is the index that is used in the European Union countries to identify the crop's condition. So we use a VH signal from Sentinel-1. So the green line is just raw data, and the red line, the dotted red line is moving average. So we can see the moment when there's only the soil, so the soil moisture variability is changing without the crops. Then we know where was the exact cultivation of the soil, and then we was analyzing the BBCH index together with in situ campaign of. So we was analyzing the condition on the field of the crops, and we can saw when the pH is increasing from the very low level to the very high with the final stage of the crop, and this is represented by the imagery from satellites Sentinel-1 when you can see that the green values on the plot are increasing. This means that the phenology phase of the crops is also increasing in the same time, and this is nicely represented with the moving average of VH signal. All those data that we was analyzing and gathering in WATERAGRI was also stored and aggregated in Agricul's decision support system, and our farmer was very happy to use this. He was implementing all the activities that he's doing on the field, mostly to have an information, to get an information in the future how different decisions, depending on different conditions of weather and soil and crop rotation, how they at the end how they affect the amount of the yield, which is for the farmer the most important factor for our farmer. And the farmer still is using this platform, and he is very satisfied with that. So the next action that was also done, most for as also a part for future modeling, was creating drainage system based on photogrammetric data. So we make an interview with the farmer, we analyze the GNS measurements for known ends of the drainage and pipes, and we make flights, and we create the data with the elevation model and with tier and RGB data. All the data are open and they are available on our repository on UPWR, and you can access it by the QR code. And based on those flights, one of the action was to identify the drainage as well with the failure of the systems. And this is example of the one field when you can see the detection of the drainage system and the potential identification of the areas where the system is from some reasons damaged. Next, based on a very precise digital elevation model that was made during the WATERAGRI project, we also identified the surface runoff to identify the critical points that where the water is always storing for too long, and this can be probably the place where. So this is one of the results. And after we take those lab analysis and analyze the images from satellites, and we have our own digital model, we started to create an integrated subsurface models. Here I am presenting the 1D simplified model that was made to analyze the efficiency of the water retainer with the inverse approach. So we structure the mesh elements, the mesh structure, and then we do the simulation over the one of the experiments that was conducted in 2021. And as a result, you can see that how in different iteration, how this water retainer kind of was probably changing the properties of the soil, that different color is a different iteration of the calibration. And after each calibration, the fitting of the curves was more close to the observation than to the model. We can see also how the water drowns during the summer, and how much the precipitation involved in a very shallow layer of the soil. The next model that was also made for the WATERAGRI project was the 3D integrated model made in hydrogeosphere, where we integrated the surface structure with the geology and the drainage system with the river and the piezometers, humidity sensor measurement, outflows. Everything was set up in one big model for the catchment, for the agricultural catchment purpose. And one of the goals was to analyze differences based on the historical data between dry, normal, and wet year. And as you can see, for the Polish condition in the last 30 years, the precipitation varied between less than 400 millimeters to even more than 700 millimeters. And based on that, the different distribution of the water in the catchment is seen. The second purpose for this model was to analyze where are the places that needs to be irrigated, and in the same time there are any places that need to be drained. So you can see that there's 4 spots that during the simulation they are constantly having high saturation, and at the same time on the right panel you can see the places that just after the very high precipitation that was over 20 millimeters, big areas with the very low saturation that drops below 0.3. We validate this model with PEST software, and you can see that the hydraulic head of the piezometers that are located in the catchment is very well corresponded to the results of the model. And on the side, one thing that I personally very like was adaptation of the Agri series game, and was made by Ashna from TU Delft. So we make a Polish version of this game that was made by Kamila Pawłowska from our university, and we create online video materials, instructions, how to play the game, how to engage people in 2 different languages, so everyone can just watch the video and start playing. So what we do with this game, we also use it for the workshops. That was in the breaks between the presentations. Sebastian was saying that we was organizing a lot of workshops, and we were trying to engage farmers, but also young people that mostly in our case in Poland was the kids of the farmers, and we was showing them solutions, and on the presentations as well they were able to test those solutions during the game. We also the game was also implemented in the teaching process at our university, both in English and in Polish version. And what for me is most beneficial as a result of the WATERAGRI, that thanks to the project, we was also able to continue our cooperation with the farmers. So the person that the project is focusing the most was so satisfying that decide to work with us in the future projects that we was able to get and cooperate for a longer time, that those results can stay for longer. So we get 2 other projects that are financed by the Horizon Europe, as well for WIF initiative, that is cooperation between National Science Center and the Swiss National Science Foundation. So thank you for your attention. Dziękuję za uwagę, and for anything that is needed, I can ask any questions.
Thank you very much, Arkadiusz. We have a question regarding the game. Where we can find this game?
So the game, I don't really know how. So the game, we have the game. We can share it if it's needed. We have 20 pieces in Polish and in English version, and we are very kind to share the game if needed. If needed, we also can produce more more pieces of this game if there will be a need. So if you will watch the video and you think that the game is interesting and you can learn or spend a funny time with it, just you can contact us and we will think about it, how to do it properly. I hope this is maybe too much to say, but yeah, we can share for sure. We can share our pieces with everyone that wants to look.
I may follow up on this. Again, please visit our website, wateragri.eu, and you can also read about the game, Agri Lemma. It was done by TU Delft and, of course, cooperation with other colleagues. As Arkadiusz said, we have 4 produced sets with, with wooden elements. It looks like a real board game from the store. However, there will be published version for your for do-it-yourself version online. So there will be a PDF version with instructions how to create your own elements. And if you have access to, for example, 3D printer, then you can go wild and create very nice elements of the game, or you can use a paper and print it on the cardboard and use cardboard elements. So it's up to you. But as Arkadiusz said, we have 4 production sets that we can share with partners who would like to test the game. We have another question. What was the interest success rate of such model by farmers?
Can you please repeat it, because I think I lost connection for a bit.
What was the interest success rate of such model by farmers? So how many farmers were interested in such model?
So for now, we can say that we test this model with our farmer, and he's happy with the cooperation. But we also in Poland, and thanks to those stakeholders' engagement, we have been asked to share the solutions to another farmer in different part of the Poland. So we can say that we are also testing the solutions of the WATERAGRI with another farmer that is not involved in the WATERAGRI, but he was interested in a testing of the solutions. So for us, it's like 2 big farmers that was kind of want to work with us directly.
Thank you, Arkadiusz.
I received some technical questions. One very detailed one first. What is this EU index BBCH? Can you explain a little bit what that is?
In principle, this is the index that explains the condition from the sprouting to the end of the vegetation process in a norm of 100 different, let's say, stages of the plant. So you can say that some numbers represent just crop after the sprouting, then when they have the flowers, and when they start to be green, and then when they start to be ready for a harvest. So this is like a unified norm of assessing the condition of the plants. You can easily find it in every language, probably, if you want to use it, and to try to assess the same stage of phenological phases in your farm if it's needed.
Okay, thank you. I have a different type of question here for you. You've been using a 3D model which seemed to remind us about the model presented by Harijan in the previous talk. Can you compare those 2 models? Are they very similar, or there are some differences?
Those models are based on the same physics, let's say, but they are from the different developers. So I don't know how much we can compare those 2 models, but in some terms of activities, we was also trying to investigate the same things. What Harijan was showing previously was mostly about data assimilation, which was based on running multiple simulation in the same time, where my models was based on one run, which was calibrated based on differences between measurement and the result of the model itself. So the approach is kind of different. But the physics, besides on the models, is the same. But the approaches were different.
I have one more question here about the application of these solutions or methods. What about the satellite data? What is the idea for applying those for the single or multiple farmers? How is this application supposed to work, and what is required in terms of knowledge and money from the farmer?
So for our farmer, the surface soil moisture was used directly to plan the sowing and to plan the cultivation of the when the farmer is investigating it in person, and when we have a good satellite images that can represent properly the conditions that are, let's say, located 20 kilometers from our site. You can look at by your phone, and you can decide it if you want to, when you want to plan the activities on the farm, as well if the conditions are not yet satisfying. Based on the previous years, you can say, okay, if now we have those conditions and they are bad, in 4 or 5 days I can plan my activities, and they will probably be placed well in the time. And like when what I learned with cooperation with farmer is that nature is never waiting, so they very often need to react in a days, and they never know what will happen in those 4 days, and those giving them 5 or 4 days of planning is very much for our farmer at least. And also when you can assess, so this is about the soil moisture, surface soil moisture, and about the phenological phase. Based on the satellite images, you can say that the plants maybe not grow properly, and maybe there is a need of giving extra irrigation or extra fertilization to save the farm, the yield.
Thank you.
We have another question, but it's also related to a little bit to our next speaker. So maybe we can ask the same question later. What are the benefits of water retainer in your study area? Do you think the model you set up verify the case study experiment results?
So in one case, we can say that those product is working, but on the other side, the economic benefits are kind of too low in terms of the cost of the product. So the benefits in the current state of the climate, we can say that the water is available or is cheap enough to be better solution, but we don't know what will happen in the future. And those types of project, I think, are made to prepare us and to give us solutions that when the current state will be not so correct, then those technologies will be maybe cheaper, or the water will be maybe more expensive, and the benefits, economical benefits of application of those technologies will be more on the date than they are maybe now. But to say it for sure, we need to analyze them to be sure how they are working and what is the possible error that cannot work when you are testing the solutions.
Thank you very much, Arkadiusz. We don't have other questions to that session. We are still waiting for our colleague Tamara Aveland, who is our next speaker. She's in South America, so a different time zone, probably 4 a.m. in the morning or 3 a.m. So we will continue our presentations, and we will pass the microphone to Ida Sarnowska from the Agriculture Advisory Center in Brwinów. And Ida will tell us a little bit about a massive open online course on WATERAGRI solutions. So Ida, please tell us more about this exciting educational resource.
Hello, good morning, everyone. I will today shortly tell you about the massive open online course on WATERAGRI solutions. And what is such course? Okay, this is a course on simply saying about all the solutions that we developed in WATERAGRI project. It's available for everyone. It will be online very soon. And you can easily access it, and I will tell about accessing it soon. The idea behind the course is to share the effects of the WATERAGRI project and disseminate the developed solution to as many recipients as possible, and therefore support sustainable agricultural production in the face of climate change challenges in Europe. And here you have a screenshot of part of this presentation. The course is dedicated to farmers, advisors, students, scientists, and all interested attendees. And for scientists, because the course is dedicated to general public, so for people who want to gain more scientific knowledge, additional materials like research papers and deliverables of the project, fact sheets, and partners' website will be linked. So if you are thinking of joining this course, you can take a look at the areas of interest, improving water retention and nutrient recycling in soils, so basically the WATERAGRI project interest, sustainable agricultural development, preventing negative effects of climate changes, water purification, and new technologies used in agriculture. So shortly, our WATERAGRI MOOC characteristics. We described 15 solutions of WATERAGRI project in over 200 slides, but don't worry, it's not just text. It's many examples of images, figures, photos, and it's explained very simply. So we show basic knowledge about the solutions, and as I said before, we link some additional materials. And the course ends with a short test, and you can gain a certificate of attendance by CDR, so by Agricultural Advisory Center in Brno. How do you participate? First, you register on our Moodle platform. The link will be given to you shortly at the beginning of the May, when we are all finished with the course. Then you join our course. You learn from the materials prepared especially for you. I estimate it's about 3 hours of learning if you really focus on what's written there. Then you pass the short test and you get the certificate. So what especially are the course contents? There are 7 presentations, 7 separate modules. First is introduction to hydrological problems in Europe. So why do we even talk about all these solutions, what we want to achieve? Then it's a presentation about WATERAGRI project, the objectives and the achievements. Then we have 4 presentations on WATERAGRI solutions grouped in categories. And for each solution, we have it described as following: shortly about the solution, like introduction to the solution, then more deeply, how does it work, how is it constructed, what are the mechanisms, how does it work, then predicted benefits of this solution, mostly focusing on water retention and nutrient recovery, but also environmental benefits and other benefits, economical benefits. And then we have part of practical application in costs. So is the solution ready to use? How much would implementing it cost? Where you can implement it? And then we have this part for scientists to learn more, where the additional links are given. And then the last presentation of the course is a short summary of all what was before. So what are these 4 groups, if you don't know yet? First group of solutions is water and nutrient management for smart and sustainable agriculture. The second group is on-site water retention solutions. Then we have on-site nutrient recovery solutions and laboratory scale tests and field scale tests. So I wanted to give you a small peek into the MOOC to encourage you to join. Here we have just a few slides of wetlands, farm constructed wetlands for nutrient recovery. So this is the first slide. Then we have, as I said, this model of construction of the course about. So basic information to introduce this solution to you. Then we have a little more deeply described how the solution works. This is also one slide, so there is many, but just to show you. Then predicted benefits for nutrient recovery. Then we have another slide for benefits for other benefits of this solution. And at the end, practical application and costs, so that you can gain knowledge if you would be really interested in applying this solution on your farm or somewhere. And then there are additional links. The WATERAGRI course will open on May 1st, so very soon. The link will be available on the WATERAGRI website. We'll inform you about that. And thank you to all the partners who supported us in creating the course, for your materials, for your reviews. We are very happy that we could work with you. Thank you very much.
Thank you very much, Ida. I have some additional questions about the language of the courses. Is it in English, or are the local languages available as well?
No, it's only in English.
You already answered where it will be available. It will be available through our website, so wateragri.eu. We had a question about certification, but you already responded to that. Do you have other questions?
Yeah, we received a question about is it possible to make shortcuts here? You mentioned you estimated a time to go through the whole thing, the whole MOOC in a linear fashion to 3 or 4 hours. If one is interested in a specific solution or group of solution, is it possible to make shortcuts in the course?
Well, yes. If you are interested in gaining information, then you can join the course, and just there will be list of presentations grouped in these categories, as I mentioned, and solutions, like the specific names of the solutions, you will see them, which presentation contained the solution. Then you can just go to this separate part of the MOOC. So if you are interested in something in specific, then of course you can jump through the parts of the MOOC as you wish. But for the certification, the test contains questions about all of the solutions. So if you want to get the certificate of attendance, you should carefully, with focus, read the whole presentations.
Thank you.
Thank you very much, Ida. The course looks amazing. So thank you very much for all the hard work that you put into creating this. So we have our next speaker already with us, Tamara Avalan from University of Oulu. And Tamara will discuss assessing the sustainability of WATERAGRI solutions using the example of the water retainer product and the farm constructed wetlands. Tamara, thank you very much for joining. I know that you are in some crazy time zone at the moment, and we are ahead of time. So sorry for putting additional stress on you. And yeah, the floor is yours.
Thank you, Sebastian. I did get up ahead of time thinking that things might go different than planned. So I am well awake. You see, I even got some lipstick on just for you. So good morning to everyone. Really interesting to be in this format. And I will be telling you about the sustainability assessment that we did in WATERAGRI. And so I guess the first question is, what do you guys know about sustainability? What do you think sustainability is? We will go a little bit into detail about this in here, but you can find a lot more information also about all of the sustainability assessments that we did in the deliverable. And so what is sustainability? Sustainability has a long history of where it came from, and is often also used sometimes interchangeably with sustainable development, which is this famous definition down here, where humanity has the ability to make development sustainable, to ensure that it meets the needs of the present without compromising the ability of future generations to meet their own needs. It is usually defined in 3 dimensions, which you can see here at the top right-hand corner: economic, social, and environmental dimensions. And we will see throughout the course, throughout this presentation, how challenging it is in sustainability assessments to really address all of those 3 dimensions. Sebastian, are you making fun of me? Oh, I can see you're fiddling with a hat there. Yeah. So you may have seen this already. In WATERAGRI, we tested a lot of different solutions in 10 different sites across Europe. And for the sustainability assessments, we focused on 2 sites and 2 types of solutions. So we looked at farm constructed wetlands in Italy, and we looked at the water retainer product and its application in Poland. And in Poland, we undertook 3 different kinds of sustainability assessments. There is a variety of sustainability assessments out there, and the partners that worked on this chose these 3. So the water footprint analysis, the cost-benefit analysis, and then a life cycle assessment. And on the farm constructed wetlands in Italy, we looked at life cycle thinking in a bit more holistic manner. And the partners there looked at life cycle assessment, life cycle costing, and a social life cycle assessment. From the types of assessment that you can see here, you may already get an inkling that the focus was largely on environmental sustainability and economic sustainability. And indeed, only in the farm constructed wetland in Italy, we were able to introduce the social life cycle assessment, which looks a bit more strongly into the social dimension of sustainability. Whereas in Poland, it was very challenging, and we ended up giving up the idea eventually of looking into social indicators. So let's look a little bit more in detail into what we did and what we found out about the water retainer product in Poland. And I guess I didn't animate this properly, but the point was to show you that this was done in 3 different plots. And the product is then sprayed on the fields. And in 2021, when we looked at the first round of spraying, the field that was looked at was planted with oats. Oh, there you go. Now you can see actually the images. And in 2022, we looked at a field, so maybe it does the same thing. No, it doesn't, unfortunately. This I didn't animate properly. we looked at a field which was next door, nearby, and there we looked at barley and wheat. The reason why I've got this table in front of you, or on top of this, these images, was to show you that there were different types of soils that we looked at, and also different types of crops. And then on top of that, there were different applications, different amounts of application of the water retainer. So no water retainer applied, or 10, respectively 15 liters of water retainer per hectare that were applied. So there were a variety of different scenarios that we were then able to look at. The water footprint analysis basically looks at how much water is taken up by the crops, and partitions this into 3 footprints, into a green water footprint. So this is how much water comes from the rain and is then being taken up, the green water footprint. The blue water footprint, which is if you put irrigation on top, how does that then look like? And the gray water footprint, which is the effect of the fertilizer and the runoff from that. And in total, this then gives you the total green water footprint. And this is really a pity. I must admit, my animation sucked this time. The point was to show you that the application of the water retainer did yield higher yields. So you did get higher yields. However, it didn't offset the entire production costs, and we'll see that also in the cost-benefit analysis. But what we did see with the water footprint is that all of the green water that was available was consumed by the crops, and that, however, that there was quite a lot of runoff with nutrients that came from the field. And this, for us, was quite interesting also looking at it from the policy perspective, because the farmer really did do a good job in being within the nutrient directive. But as soon as you then look into the Water Framework Directive, the stream that this runoff was leading into might have been impaired with the amount of nutrients that came from this runoff. So also interesting to then think about how can we streamline different policies in Europe so that farmers aren't in this awkward position of abiding to one rule but then violating another. The cost-benefit analysis, which was the second assessment that we looked at, does a financial analysis. So it looks at the costs and benefits for the farmers, but it also looks at the costs and benefits on an external perspective. And the decision rule is that a project is profitable if the benefits exceed the cost on a societal level. And then you see the formula of how this is done below for being complementary. What the cost-benefit analysis showed, and I will animate this properly and then maybe put this online in below the YouTube link so that you can see the numbers below. The cost-benefit analysis showed that the return on investment, so the green line that you see below, was usually negative. So the return on investment wasn't really good enough. The costs of the water retainer did not offset the increased revenue that one would get from the increased yield. So as I told you in the water footprint analysis, we already saw that the yield did increase with the water retainer product applied, but the costs for spraying it and putting it on the field were too high to offset those increased yields. What we did see, however, is also that the increased yield may create a positive externality, since the carbon footprint per kilogram of cereal becomes lower. You have a higher yield, Thus, you have a lower carbon footprint per production. For the life cycle assessment, we chose a system boundary that was really subject to the field. So we didn't look at the production of the water retainer outside of the field, and we also did not look at the downstream activities, so at the removal of the produce and what happens with the crops, etc. So the system boundary really was the field and the application of the water retainer on the field. And here, similarly, the effect was largest on the climate change total. So we did see that the water retainer can reduce the environmental impact, but the magnitude really depends on crop type and external factors such as soil type. We did see quite a large effect of soil on yield and also on the effect of the water retainer on that yield. We could see that a higher dose of the water retainer leads to a better environmental performance, but in the life cycle assessment, these changes were really quite minimal. And so we couldn't really come to a good conclusion from the life cycle assessment. What we can say about the water retainer on the Polish site is that there was a yield gain, and so we can acknowledge the effects on the environmental dimension of sustainability. But we also saw from the cost-benefit analysis that the economic dimension was negatively affected or did not have the positive effect that we would have expected or wanted. And we couldn't really say anything about the social dimension because we couldn't recover any information on this. So we cannot ascertain with certainty that the water retainer can be recommended for sustainable farm use. We would need more information to be able to do that, in particular in the social dimension. Now, if we look at the farm constructed wetland at the Italian site, here we had a rather large system. And as I explained, we did 3 different kinds of life cycle analyses on this. And this was the system boundary. So you have an open wetland area, which or an open field, which receives in part irrigation that drains into the wetland that you see on the left. And if there wouldn't be a wetland, then this would be discharging directly into the groundwater and largely into the river system and become also potentially a non-point source of pollution. And with the wetland in the middle, this then gets treated and is then discharged through a system of ditches into and is then fairly clean into groundwater and into the river. The system boundaries here were looking at the 2 phases, the construction phase, so putting in the wetland, as well as the operational phase while the wetland is running. It did not look at the dismantling phase that was considered to be neglectable with respect to the effects of the construction and the operational phase. The assessment yielded 3 results, and then those 3 scores were also integrated. On the environmental score, there was a fairly positive score of 45 out of 100. On the economic score at the bottom left, there was a negative score, and in particular that has to do with the construction, the costs of the construction and the operation of the wetland. And then there was a very high social score. And this is mostly due to the fact that this wetland in particular is used for training purposes of the University of Bologna, and thus produces positive effects for students, as well as creating jobs in the region and creating awareness for other farmers in the area. So this then yields a total integrated positive score. And I guess this is to show that in contrast to what we saw in the water retainer, where we didn't have a social score and we had a similar picture of a positive environmental score and a potentially negative and negative economic score, the social score might have actually changed the entire picture of the recommendation, as we see here, where we have a very high social score. And the social score being, or the social dimension of sustainability often being overlooked, is what we're saying out of this project, that may need more attention. So in a summary for the constructed wetland, while the most amount of environmental damage is caused in the construction, the highest costs occur for the maintenance and operation, with the assumption that the system has a lifetime of 30 years. The wetland does reduce freshwater and marine eutrophication risks, and thus has a positive environmental score. But this can again not offset the costs for maintenance. And as I said, the social score comes from the training and the workers that then get employed for this wetland. What we then also did in a smaller assessment on this wetland was to provide some indications of incentives and subsidies to be put in place to incentivize the construction of constructed wetlands for farm use. And in summary, we then kind of were able to say that on the one hand, we couldn't recommend either of these systems because the water retainer didn't have a full picture, and the constructed wetland was a rather unusual case of wetland system used for training purposes mostly. But overall, we could say that irrigation management systems, constructed wetlands, and the water retainer were definitely solutions that will be interesting or are interesting for farmers to look at. So that's the icon at the top. Constructed wetlands were also interesting for researchers, which are the ones in the middle, as well as for advisory services, which are the icon at the bottom. And other systems might then be more potentially more interesting in the future for farmers, such as the ones in italic called here drainage systems, bio-based membranes, and microfluidics. So with that, I would like to thank all of the people that did the hard work in the sustainability assessments, which are mentioned here, and really show gratitude for having been part of this project for the past 4 years. It kind of does feel a bit sentimental that it is coming to an end. So there you go. Thank you very much.
Thank you very much, Tamara, for your comprehensive presentation. We are now ready for a Q&A session, the last session. So please ensure that your questions are submitted if you're using a Menti application. We have already a few questions.
Okay. Yeah.
Go ahead.
Do you want to do it? Or yeah, okay. So we have here questions for you about the social sustainability. You mentioned your analysis for the wetland in Italy, but you said you had some issues with the collecting data in Poland. But the question here is about what type of social sustainability factors were you, how can you say, expecting to find for the water retainer, and what kind of data was it that you would have needed for the analysis?
Yeah, social sustainability, it's social, so you kind of got to talk to people. And in this case, or often what one would want to do for the social dimension of sustainability is to talk to all of the different sides, all of the different stakeholders that are involved with this product. So in this case, this would have been the producer of the water retainer, as well as the farmer, advisory services, and others, and then ask them about things like willingness to pay, acceptance of the product, things like we then also looked at in the constructed wetlands, impact on people in terms of increased wages, interest in the product, opportunity for learning from its effects, So those would have been the kinds of things that we would have liked to be able to do in Poland, but we realized that in part we had language issues, and in part we had also issues reaching the company. And so this was then considered to be too complex to address in the time frame of the project.
Okay, thank you.
Yeah, we don't have any more questions. So thank you very much, Tamara, for this heroic presentation at 3 a.m. or 4 a.m. And
only 6.
6 a.m. 6 is already morning. Thank you very much. And we move on.
Okay. Thank you, Tamara.
So Rolf, back to you.
So we have no more presentations.
Yes.
So what am I supposed to say? Yes, we are ahead of schedule, but we'd like to thank everybody who listened in and who watched the presentations. Thanks to all the speakers, the participants, and everybody involved in the event today. So again, we'd like to remind you about the like the WATERAGRI website and also our YouTube channel. If you missed some part of the today's program, you're particularly interested in one of those presentations, they will be available through our YouTube channel. And there will be some last final updates in relation to our project. I think that's all that I have to say. Is that correct?
Yes, so we encourage you to visit our website again, wateragri.eu, when you find all the information about the project, all the deliverables. Soon there will be a MOOC link to it, but also the data will be presented on demand. So you have access to everything that we have produced in the project. And for today, that's it. So thank you very much. Thank you very much for all the guests on YouTube. Have a wonderful day and hopefully see you soon.
Okay. Bye-bye.